All right, so implicit differentiation is what we like to call the lazy man's derivative. Okay, so in order to take a derivative, what you normally want is you want your function to be solved for y. Okay, um, but sometimes it can be really difficult to solve for y. So what we end up doing is using implicit differentiation to help us do that process. Okay, so for example, if I were to tell you, here's a function y equals x squared plus x minus 2. If I were to tell you to take a derivative of it, you shouldn't have too much of a problem, right? Y prime is 2x plus 1. Right? And I'm done. Like, no big deal. Okay? But what if I gave you a function that looked like this? Let's say x squared y equal to 1, right? And I want you to solve for x and then take a derivative of it. So if I wanted to solve for x, then what I would do is I would say x squared is equal to 1 over y. And then I would write x is equal to plus or minus the square root of 1 over y. And now the question is, well, what do I take a derivative of? Do I take the derivative of the positive square root of 1 over y? By the way, you can't do this. If you're wondering, like, wait a minute, why am I taking derivatives of of y's? We're supposed to take derivatives of x's. No, you just change the way it looks. So, for example, over here, you would have written dy dx. For this problem, you actually would have used dx dy, right? Because you're taking a derivative of x with respect to y values, right? So you can change that around. It just depends what equations we're using and what variables we're using. But you can do like dx dt, dy dt, anything else, d theta dt. It just depends what's on the actual problem. But notice, we're left at a bit of a question as to which one do I take a derivative of, the positive one or the negative one, right? So that makes it a little bit tougher. So what we do is we say, forget solving for x. I'm just going to take the derivative the way it looks like right there. Okay? So how do we do that? Well, it's called implicit differentiation. Okay, we're going to do this implicitly. So let me kind of show you what that's going to look like. I guess, let me put it right here. It's not really like a definition, but it's more of you telling people what you're doing. So let me see if I can explain it to you. So let me give you an example, because I think the best way to kind of see this is by using an example. So I'm going to take a derivative of the following, okay? X squared y equal to 1. And I'm going to do this implicitly. Now notice, x squared y is a product, correct? Two things being multiplied together. So if it's a product, I have to use the product rule. So let me just put some directions to this. Find dy dx, okay? Find dy dx. In other words, take a derivative with respect to x's. Okay, you're going to be taking derivatives with respect to x. That means the x's are the things you're taking derivatives of. Okay? And you have to make sure you mention it if you ever take a derivative of something that's not an x. So let me explain let me show you what that looks like. So here we go. So, x squared y, that's a product. So according to the product rule, what I'm supposed to do is take a derivative of x squared first, correct? X squared first. So what's the derivative of x squared? 2x. Okay, now I took a derivative of x, right? And notice I'm supposed to take derivatives of x, right? The dx on the bottom right there. I'm supposed to be taking derivative of x. So if I take a derivative of the correct variable, then great. I did what I'm supposed to do, no problem. Remember, it's derivative of the first function first times the second function, right? So that's 2xy plus, write the first function, x squared, and then take a derivative of the second function. What's the derivative of y? 1. But which letter am I supposed to be taking derivatives of? X. And I just took a derivative of y. So we kind of say like, oops, I messed up. Let me tell you what I did. I took a derivative of y even though I knew it should have been an x. So I'm mentioning my process, okay, dy dx equals to the derivative of 1, that's 0. Okay, so let me clean this up a little bit. 2xy plus x squared dy dx equals 0. Now remember, they wanted me to find dy dx, right? I had to solve for it. All I have to do is move everything away from dy dx, and then I'm done. I'm going to solve for dy dx. So let's subtract 2xy to both sides. So this is going to look like this. X squared dy dx is equal to negative 2xy. And to get dy dx all by itself, I'm going to divide both sides by x squared. So dy dx is equal to negative 2xy divided by x squared. Now simplify, right? We can get rid of x's. So dy dx is equal to negative 2y over x. And there's my answer. Notice how my solutions doesn't just have x values in it. It actually has both variables. Now that's not always the case, but usually you end up with multiple variables inside of your function, your derivative function. So remember how like you'd be doing homework problems and they'd say like, oh, find the derivative and then plug in the point 2 comma 3. So we'd plug in a 2, but we never plugged in a y value, right? It was always just the x. These allow for both. Okay? You can put the x and the y value for your points. So it's not like you're doing derivatives in a, it's not like you're learning brand new definitions for derivatives. We're still using the same definitions of power rule, product rule, quotient rule, stuff like that. But it's just, we're allowing ourselves to take derivatives of anything we want. Okay? Any letter. Anything at all. So just to give you a kind of silly example here, if I were to write, let's say 3a squared plus 6b plus 10c to the 4th equals 5, and I tell you, find, say, db, hold on, let me see. Yeah, let's find db dt. So what variables am I taking derivatives of? T. Do you see any t's there? Well, obviously you don't see that one. No, I'm just kidding. No, there are no t's in that example, right? So that's okay though. I can still take a derivative. Okay? So what is the derivative of 3a squared? What is it? 6a. And was that a t? No, so I gotta say dA dt. Okay, what's the derivative of 6b? 6. What do I put after? dB dt. Plus, what's the derivative of 10c to the 4th? 40c cubed. And that's dc dt. And then what's the derivative of 5? 0. So all I got to do is solve for dB dt, right? So move everything. Okay, no matter how weird it looks, you're going to move everything. So I'm going to move the 6a dA dt and the 40c cubed dc dt at the same time. I'm going to move them to the right just by subtracting. So 6 dB dt is equal to negative 6a dA dt minus 40c cubed dc dt. And all I have to do now is just divide by 6, right? So dB dt is equal to, I'm going to write negative 1/6, okay? Just to not make it such a big fraction. So negative 1/6. This is going to be 6a dA dt plus 40c cubed dc dt. And there's your answer for dB dt. Now, if you're like, this makes no sense, what exactly am I doing? It's prepping us for related rates. Because what's going to happen is there's going to be like a problem at some point where they're going to give us, like, let's say a cone. Okay? And, you know, to a cone we have a height, right? A radius. And they're going to tell you the rate of change of the height with respect to time is the following. The rate of change of the radius with respect to time is the following, right? You're going to be getting things assigned to certain variables, and when they write dH dt, if that's height, that means that the height is changing. It might be getting taller, it might be getting shorter, depending on what's happening, right? If that cone represents gravel, and there's a gravel belt above it, and it's dropping gravel on top of it, that means that cone's going to keep getting bigger and bigger and bigger over time, right? So how fast is it growing? Well, that's dH dt. It's the rate of change of height over time, okay? Maybe the radius is getting bigger as well, because as you drop more sand or gravel or whatever, the diameter is getting bigger, so the radius is getting bigger. Well, how fast is it expanding? Well, that would be dr dt, right? They're trying to get you guys to understand that variables can change over time. Okay, that's what section 2.6 is. Okay, implicit differentiation just tries to introduce the idea of this notation, right? dB dt, dA dt, dC dt, dy dx, dx dy, right? You can change it to whatever you want. d theta dx, d theta dt. Those things exist, and their meaning is rates of change, right? The dH dt means the rate of change of h with respect to time, right? So they're just trying to get you to understand this exists, so that when you see it in section 2.6, it's not like, what is it? I've never seen that notation before. Like, you would have been used to it because of implicit differentiation. Okay? So, let's do this example here. I know this is kind of like example 3, but this is what I have as my example 1, just so you guys know. The other stuff was just kind of like us kind of messing around, trying to dip our feet into this thing. So find dy dx given, and we'll put x squared minus 2y cubed plus 4y equals 2. So let's go ahead and do that. So we're going to take a derivative with respect to x, right? dy dx. We're going to take a derivative with respect to x. dx on the bottom. See, dy dx makes sense if I had it solved for y. But notice, is this going to be easy to solve for y when I have a y cubed? No, right? Cubics are always kind of tough to solve. Maybe not always, but a lot of times they are kind of tough to solve for. Okay? So instead of kind of racking your brain and trying to figure out how should I simplify it so I can get y by itself, we're just going to say, who cares? Let's just take a derivative. I can do it, right? So let me answer the phone. All right, so let's take a derivative here. Okay, so the derivative of x squared is 2x, right? I'm supposed to be taking derivatives of x's, so should I write dx dx? No, right? That doesn't make any sense. If I write this, then this just cancels. So it goes away. So there's no need to do that whenever you're doing the correct variable. Now, minus 2y cubed, 6y squared, dy dx, right? I took a derivative of y when it should have been an x, right? Plus, what is that? 4 dy dx equals, well, that's 0. Now I got to solve for dy dx, but it comes out twice. Now, thankfully, we know of a thing called factoring, right? Since they have the same term, we can factor it out. But before we do that, let's get that 2x over to the other side. So I'm gonna move that over to the other side right now. So it's negative 6y squared dy dx plus 4 dy dx equals negative 2x. So now I'm going to factor out the dy dx term, okay? So dy dx times, I'm going to write 4 minus 6y squared, okay, just to make it positive in the front. So to solve for dy dx, I'm going to have to divide both sides by 4 minus 6y squared. So my final answer here is going to look like this. Negative 2x, 4 minus 6y squared on the bottom. And there's my derivative of that function. Like I said, we like to call it the lazy man's derivative because we don't care about solving for y. I can take a derivative of anything. Just show me the equation, tell me what you want me to take a derivative with respect to, and I can do it for you. I don't have to solve for any letter or anything. I'll just start from whatever it is you give me. Okay, I'll just do it like that. So what I'm going to do is I'm going to give you a couple problems to try. Okay, I'll stop the video just so that you guys can have a little bit of time, and then we'll kind of check the answers. Okay, so here we go. Let me see. Differentiate. And the first one is going to be I want you guys to do these on your own, or consult a neighbor if you want. And here's one more. Alright, so I'm going to pause this, give you guys some time, okay? Alright, so we start off with something that's kind of on the easier side, right? I'm supposed to take a derivative of y squared with respect to x. Notice it's not the right variable, right? So when I take the derivative of y squared, I get 2y, but I took a derivative of y when I should have been taking a derivative of x, so I got to put dy dx, okay? And that's it. That's my derivative. Okay, so it's 2y dy dx. Okay, now for part B, I'm taking a derivative of x plus 2x squared plus y with respect to x. Notice there are 2x variables there out of the 3, so 2 out of the 3 will not require me to do a mention, as we call it. The derivative of x is 1. the derivative of 2x squared is 4x. But again, I don't have to write dx, right? That's just redundant. No need to do that. But the derivative of y is just 1 dy dx. Okay? So that would be your answer. If you want to clean it up just a little bit, it would look like this. And that would be your solution for that. Are we okay with those two? Yeah? Anybody not okay with those two? All right, so let's look at this last one. So product rule, right? I have to take a derivative of x squared y cubed with respect to what? Y, okay? So y is the correct variable. So when I do this product rule, the derivative of x squared is 2x, but that's not the right variable. So I got to write dx dy. Okay, times y cubed plus, rewrite x squared, times the derivative of y, which is 3y squared. So that's my derivative. I'm just going to kind of clean it up a little bit. So this will be 2xy cubed dx dy plus 3x squared y squared. And that's your answer. Okay, so on Monday, we'll continue this lesson and we will go over the quiz that you guys took.